NENOMATICA, where mathematics meets YouTube excellence. Exponential equations. Welcome to this tutorial on solving exponential equations. Today, we'll solve the equation shown on your screen using properties of exponents. Let's start by isolating our exponential term. First, we'll move the constant 2 to the right-hand side by subtracting it from both sides. This gives us -2 on the right. Next, let's rewrite 8 as 2 to the power of 3, since this will help us simplify the exponential expression later. Now, let's simplify the right side of the equation by calculating 2050 minus 2. This gives us 2048. Let's apply the product of powers rule, which states that a raised to the m times a raised to the n equals a raised to the m plus n. In our case, we have 2 raised to the power of 3 times 2 raised to the power of 2x squared. Using the rule, we can combine these as 2 raised to the power of 2x squared plus 3. 2048 can be written as a power of 2. Since 2 to the power of 10 is 1024, and 2 to the power of 11 is 2048, we can rewrite our equation as 2 to the power of 2x squared plus 3 equals 2 to the power of 11. When we have the same base on both sides of an equation, the exponents must be equal. This gives us the equation 2x squared plus 3 equals 11. Now we can solve for x. First, subtract 3 from both sides. This gives us 2x squared equals 8. Dividing both sides by 2, we get x squared equals 4. Taking the square root of both sides, we find that x equals plus or minus 2, which is our final answer. Let's solve the following equation. The fraction 1 over 25 raised to the power of 2x times 5 raised to the power of x minus 2 equals 5. Let's start by rewriting 1 over 25 as 25 raised to the power -1. This is using the negative exponent rule, where a raised to negative n equals 1 over a raised to n. Next, let's express 25 as 5 squared, since 25 equals 5 times 5. Now, let's simplify the exponents using the power rule for exponents. When we raise a power to another power, we multiply the exponents. So 5 squared raised to -1, all raised to 2x, simplifies to 5 raised to -2 times 2x, which is -4x. When we multiply powers with the same base, we add the exponents. So 5 to the -4x times 5 to the x minus 2 equals 5 to the power of -4x plus x minus 2. Now, let's combine like terms in the exponent. -4x plus x equals -3x. So our expression becomes 5 to the -3x minus 2 equals 5. Since the bases are the same on both sides and equal to 5, the exponents must be equal. This means -3x minus 2 equals 1. Let's solve for x by first adding 2 to both sides. Finally, we'll divide both sides by -3 to get our answer. Let's look at the example problem we need to solve. Let's solve this exponential equation step by step. First, let's rewrite 25 to the x as 5 squared to the x, and 9 to the x minus 1 as 3 squared to the x minus 1. Next, applying the rules of exponents, we can rewrite 5 squared to the x as 5 to the 2x, and 3 squared to the x minus 1 as 3 to the 2x minus 2. Now, let's factor the numerator and denominator by rewriting 5 to the 2x minus 1 as 5 to the 2x times 5 to the -1, and 3 to the 2x minus 1 as 3 to the 2x minus 2 times 3. We can now factor out 5 to the 2x from the numerator and 3 to the 2x minus 2 from the denominator. Let's simplify the expressions in the parentheses. In the numerator, we have 1 plus 5 to the -1, which is 1 plus 1 over 5. In the denominator, we have 1 plus 3 to the first power, which is simply 1 plus 3. Continuing with our simplification, 1 plus 1/5 equals 6/5, and 1 plus 3 equals 4. Now, let's rewrite the expression 3 to the 2x minus 2 in the denominator. Using the rules of exponents, we can write it as 3 to the 2x divided by 3 squared, which is 3 to the 2x divided by 9. Let's now multiply the numerator and denominator. In the numerator, we have 5 to the 2x times 6 times 9. In the denominator, we have 5 times 3 to the 2x times 4. Let's further simplify this expression. We can separate the exponential terms and the numerical terms, giving us 5 to the 2x divided by 3 to the 2x times 6 times 9 divided by 5 times 4. Let's simplify the numerical part. 6 times 9 equals 54, and 5 times 4 equals 20. 54 divided by 20 simplifies to 27 divided by 10, which is the same as 15 halves. So we have 5 to the 2x divided by 3 to the 2x equals 25 ninths. We can rewrite 5 to the 2x divided by 3 to the 2x as the ratio of 5 squared to 3 squared, all to the power of x. Now, 5 squared equals 25, and 3 squared equals 9. So we have 25 ninths to the power of x equals 25 ninths to the power of 1. Since the bases are the same on both sides of the equation, the exponents must be equal. Therefore, x equals 1. Let's verify our solution by substituting x equals 1 back into the original equation. When x equals 1, 25 to the first power gives us 25, and 5 to the 2 times 1 minus 1 gives us 5 to the 1, which is 5. In the denominator, 9 to the 1 minus 1 is 9 to the 0, which is 1. 3 to the 2 times 1 minus 1 is also 3 to the 1, which is 3. So our left-hand side becomes 25 plus 5 divided by 1 plus 3, which is 30 divided by 4, or 15 halves. This equals the right-hand side, 15 halves, confirming that x equals 1 is indeed our solution. In summary, we have solved the exponential equation by using the properties of exponents, factoring out common terms, and simplifying. The key insight was recognizing that we could rewrite the terms to isolate the exponential expressions, which led us to the solution x equals 1. Today, we'll solve an interesting example that involves a clever substitution technique to transform a complex exponential equation into a simple quadratic equation. Let's look at our example problem. We need to solve the following exponential equation. 3 raised to the power of 2x squared minus 6x plus 3, plus 6 raised to the power of x squared minus 3x plus 1, equals 2 raised to the power of 2x squared minus 6x plus 3. This looks quite complex, but we'll solve it step by step using a special substitution technique. Step 1. Let's rewrite the exponential terms by separating the constant parts. For the first term, we can write 3 to the power of 2x squared minus 6x plus 3 as 3 cubed times 3 to the power of 2x squared minus 6x. For the second term, we can write 6 to the power of x squared minus 3x plus 1 as 6 to the power of 1 times 6 to the power of x squared minus 3x. For the right side, we can write 2 to the power of 2x squared minus 6x plus 3 as 2 cubed times 2 to the power of 2x squared minus 6x. Step 2. Now, let's calculate the constants and rearrange the equation to standard form. 3 cubed equals 27, 6 to the power of 1 is just 6, and 2 cubed equals 8. We'll also move everything to the left side of the equation to get 0 on the right. Notice that we can rewrite the expression for the exponent of 3 as 2 times x squared minus 3x. Also, the second term is actually the product of 3 and 2, each raised to the power of x squared minus 3x. The third term has 2 raised to the power of 2 times x squared minus 3x. Step 3. To simplify further, let's divide all terms by 2 raised to the power of 2 times x squared minus 3x. For the first term, we get the fraction of 3 to the power of 2 times x squared minus 3x divided by 2 to the power of 2 times x squared minus 3x. For the second term, we have 3 to the power of x squared minus 3x times 2 to the power of x squared minus 3x, all divided by 2 to the power of 2 times x squared minus 3x. The third term becomes simply negative 8. Step 4. Let's simplify the fractions. In the first term, we have 3 over 2, all raised to the power of 2 times x squared minus 3x. In the second term, the numerator simplifies to give us 3 over 2 raised to the power of x squared minus 3x. So our equation becomes 27 times 3 over 2 raised to the power of 2 times x squared minus 3x, plus 6 times 3 over 2 raised to the power of x squared minus 3x, minus 8 equals 0. This is getting simpler, but we still have exponential terms with different powers. Step 5. Now comes the key insight. Let's make a substitution to simplify this equation. Let's define t equal to 3 over 2 raised to the power of x squared minus 3x. With this substitution, the first term becomes 27 times t squared, the second term becomes 6 times t, and the third term stays as negative 8. So our equation becomes 27t squared plus 6t minus 8 equals 0. This is now a standard quadratic equation that we can solve using familiar methods. Step 6. Let's solve this quadratic equation. We can use the quadratic formula, t equals negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. In our case, at equals 27, b equals 6, and c equals negative 8. Substituting these values, we get t equals negative 6 plus or minus the square root of 36 plus 864, all divided by 54. This simplifies to t equals negative 6 plus or minus the square root of 900, all divided by 54. Taking the square root, we get t equals negative 6 plus or minus 30, all divided by 54. This gives us t equals 4/9 or negative 2/3. Since t represents an exponential expression, and exponential expressions with positive bases are always positive, we know that t must be positive. So t equals 4/9 is our only valid solution. Step 7. Now we substitute back our value of t into our original substitution equation. We get 3 over 2 raised to the power of x squared minus 3x equals 4/9. To solve for x, we need to get the exponents to match. It turns out that 4/9 can be written as 3 over 2 raised to the power of negative 2. Let's verify this. 3 over 2 squared equals 9 over 4, and the reciprocal of that is 4 over 9. So 4/9 equals 3 over 2 raised to the power of negative 2. Step 8. Since the bases are the same on both sides, the exponents must be equal. So we can write x squared minus 3x equals negative 2. Rearranging to standard form, we get x squared minus 3x plus 2 equals 0. This can be factored as x minus 1 times x minus 2 equals 0. Therefore, x equals 1 or x equals 2. In this video, we're going to solve an exponential equation. Let's look at our example. To solve this exponential equation, we'll start by dividing all terms by 2 to the x power. This will help us simplify the right side of the equation. On the right side, 2 to the x divided by 2 to the x equals 1. For the left side, let's rewrite the fractions. 1 divided by 2 to the x can be rewritten as 1/2 to the power of x. Now, let's rewrite the second term. 3 to the power of x over 2 divided by 2 to the x. We can rewrite 3 to the x over 2 as the square root of 3 to the power of x. Next, we can simplify the second term further. Square root of 3 to the x divided by 2 to the x can be rewritten as the fraction square root of 3 divided by 2 raised to the power of x. Now, let's recognize some special trigonometric values. 1/2 is the sine of pi over 6, and square root of 3 over 2 is the cosine of pi over 6. Now, this is a key insight. The equation sine of pi over 6 to the x plus cosine of pi over 6 to the x equals 1 has a special form. In general, for any angle theta, the equation sine theta to the x plus cosine theta to the x equals 1 is only satisfied when x equals 2. Let's verify our solution by substituting x equals 2 back into the original equation. On the left side, we have 1 plus 3 to the power of 2 over 2, which is 1 plus 3 to the power of 1, which equals 1 plus 3, which is 4. On the right side, we have 2 to the power of 2, which is 4. Since both sides equal 4, our solution x equals 2 is correct. Let's solve the following exponential equation. 3 times 16 to the power of x plus 37 times 36 to the power of x equals 26 times 81 to the power of x. Our first step is to divide all terms by 81 to the power of x. This will help us simplify the equation and get all terms on one side. Now, let's express each term in a common form. 16 can be written as 4 squared, and 81 is 9 squared. So 16 to the x over 81 to the x equals 4 over 9, all to the power of 2x. Similarly, 36 can be written as 6 squared, and 81 is 9 squared. So 36 to the x over 81 to the x equals 6 over 9, which simplifies to 2/3, all to the power of 2x. But wait, let's recalculate. 36 is 6 squared, which is 2 times 3 squared. And 81 is 3 to the 4th power. So 36 to the x over 81 to the x equals the quantity 4 over 9 to the power of x. When we divide 81 to the x by itself, we get 1. After simplifying, we can rearrange the equation to standard form as 3 times the quantity 4/9 to the power of 2x plus 37 times the quantity 4/9 to the power of x minus 26 equals 0. If we let t equal the quantity 4/9 to the power of x, then t squared equals the quantity 4/9 to the power of 2x. This substitution gives us a quadratic equation in terms of t. 3t squared plus 37t minus 26 equals 0. Now we need to solve this quadratic equation for t. We can use the quadratic formula, t equals negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. With it equals 3, b equals 37, and c equals negative 26, we get t equals negative 37 plus or minus the square root of 37 squared minus 4 times 3 times negative 26, all divided by 2 times 3. Simplifying, we get t equals negative 37 plus or minus the square root of 1,369 plus 312, all divided by 6. Further simplification gives t equals negative 37 plus or minus the square root of 1,681, all divided by 6. Taking the square root, we get t equals negative 37 plus or minus 41, all divided by 6. This gives us two values, t equals negative 13 or t equals 2/3. Since t equals the quantity 4/9 to the power of x, and t represents a positive value, t cannot be negative. Therefore, t equals negative 13 is not a valid solution for our original equation, as no real value of x can make 4/9 to the power of x equal to negative 13. So our only valid solution is t equals 2/3. Now let's solve for x. We have the quantity 4/9 to the power of x equals 2/3. We can write 2/3 as 2/3 to the power of 1. Rewriting the left side, we have the quantity 2/3 to the power of 2x equals 2/3 to the power of 1. When we have equal bases with different exponents, we can equate the exponents. So we have 2x equals 1. Dividing both sides by 2, we get x equals 1/2. Let's look at this example. We need to solve for x in the equation. 3 raised to the power of 2x squared plus 6x minus 9, plus 4 times 15 raised to the power of x squared plus 3x minus 5, equals 3 times 5 raised to the power of 2x squared plus 6x minus 9. First, let's rewrite the equation to align the exponents. We'll subtract 1 from each exponent on both sides of the equation to make the exponents easier to handle. Next, let's use the property of exponents that a to the power of b minus c equals a to the power of negative c times a to the power of b. We'll also factorize the exponent 2x squared plus 6x minus 8 as 2 times the quantity x squared plus 3x minus 4. Now, let's simplify this expression. 3 to the power of negative 1 is 1/3. 3 squared is 9. So 3 to the power of 2 times the expression becomes 9 to the power of that expression. Similarly, for the other terms, 15 to the power of negative 1 is 1/15, and 5 to the power of 2 is 25. To solve this equation, we need to have all terms with the same base. Let's choose to express all terms using the base 15. We can write all powers in relation to 15. Let's simplify the fractions. 9 over 15 equals 3 over 5 squared, and 25 over 15 equals 5 over 3 squared. To simplify our work, let's make a substitution. Let t equal 3 over 5 to the power of quantity x squared plus 3x minus 4. This simplifies the terms with the complex exponents. Now let's simplify and rearrange this equation. Let's set t squared equal to s. This gives us a quadratic equation in terms of s. Now we can solve this quadratic equation using the quadratic formula. For the equation, as squared plus bs plus c equals 0. S equals negative b plus or minus the square root of b squared minus 4ac, all divided by 2a, all divided by 2a. Now we need to back substitute to find t and then x. Remember that s equals t squared, so t equals plus or minus the square root of s. Since t was defined as 3 over 5 raised to a power, and bases in exponential expressions are positive, t must be positive. So for s equals 1, t equals 1. And for s equals negative 1.8, there's no valid value of t, since t can't be imaginary in our context. Now, let's substitute back to our original expression. We had defined t as 3 over 5 raised to the power of x squared plus 3x minus 4. Since t equals 1, we set the exponent equal to 0. Let's begin with our example. We need to solve the following exponential equation. 27 to the power of x plus 12 to the power of x equals 2 times 8 to the power of x. The first step we'll take is to divide both sides of the equation by 8 to the power of x. This will help us simplify the right side of the equation. So we get 27 to the power of x divided by 8 to the power of x plus 12 to the power of x divided by 8 to the power of x equals 2 times 8 to the power of x divided by 8 to the power of x. Now, on the right side, dividing 2 times 8 to the power of x by 8 to the power of x gives us simply 2. Next, let's apply the property of exponents that says a to the power of m divided by b to the power of m equals the quantity a divided by b, all raised to the power of m. Using this property, 27 to the power of x divided by 8 to the power of x equals the quantity 27 divided by 8, all raised to the power of x. Similarly, 12 to the power of x divided by 8 to the power of x equals the quantity 12 divided by 8, all raised to the power of x. Now, we can simplify these fractions. 27 divided by 8 is equal to 3 cubed divided by 2 cubed, which is 3 to the power of 3 divided by 2 to the power of 3. This further simplifies to the quantity 3 divided by 2, all cubed, and 12 divided by 8 equals 12 divided by 8, which simplifies to 3 halves. So our equation becomes the quantity 3 halves cubed to the power of x plus the quantity 3 halves to the power of x equals 2. To simplify our work further, let's introduce a substitution. Let's define t equals the quantity 3 halves to the power of x. With this substitution, the first term becomes t cubed, and the second term is just t. So our equation becomes t cubed plus t equals 2. Now we can rearrange this to standard form by subtracting 2 from both sides. This gives us t cubed plus t minus 2 equals 0. Now we need to factor this polynomial. We can try to find the roots by testing some simple values. If we try t equals 1, we get 1 cubed plus 1 minus 2, which equals 0. So t equals 1 is a solution, which means t minus 1 is a factor of our polynomial. We can use polynomial division to find the other factors. Since t equals 1 is a solution, and the quadratic factor t squared plus t plus 2 has no real roots, we can verify this by checking that its discriminant is negative. T equals 1 is our only real solution. So we have t equals 1. Now let's substitute back to find the value of x. We defined t as the quantity 3 halves to the power of x, and we found that t equals 1. So we have the quantity 3 halves to the power of x equals 1. To solve for x, we need to remember that if a to the power of x equals 1, then x must be 0, as any non-zero number raised to the power of 0 equals 1. Therefore, x equals 0 is our solution. Let's look at this example. We need to solve the following exponential equation. 1 plus a squared plus plus a to the power of x minus 1 plus a to the power of x equals the product of 1 plus a squared, 1 plus a to the fourth, 1 plus a to the eighth. First, let's recognize that the left side of the equation is a geometric series. For a geometric series with first term 1, common ratio a, and x plus 1 terms, we can use the formula. Sum equals 1 minus a to the power of x plus 1 divided by 1 minus a. So our equation becomes 1 minus a to the power of x plus 1 divided by 1 minus a equals the product on the right side. Next, we multiply both sides by 1 minus a. This gives us 1 minus a to the power of x plus 1 equals 1 minus a times the product on the right side. Now, let's expand the right side. Note that 1 minus a times 1 plus a equals 1 squared minus a squared, which is 1 minus a squared. We can continue this pattern of expansion using the difference of squares formula. When we expand completely, the right side becomes 1 minus a to the power of 16. Now we have the equation 1 minus a to the power of x plus 1 equals 1 minus a to the power of 16. So a to the power of x plus 1 must equal a to the power of 16. Since there is not equal to 0 or 1, which is a given condition in the problem, we can set the exponents equal to each other. So x plus 1 equals 16. Finally, we solve for x by subtracting 1 from both sides. We get x equals 15. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.